morning, everyone. This morning we're going to talk about diffusion of capillary gases. For our first objectives, we are going to define diffusion, identify the partial pressure of gases in the alveoli, calculate the ideal alveolar gas equation. This is one of those equations we will use for the rest of your respiratory careers, the P big AO2 or the alveolar air equation. This tells us how much oxygen our patient is diffusing. And we'll look at a diagram to locate the 9 layers of the AC membrane. We'll explain Fick's law in relation to diffusion. We'll look at Graham and Henry's law as well. Then we'll look how to treat various diffusion defects in the alveoli. So to define diffusion, we are going to say that it's the movement of gas molecules from an area of high concentration to an area of low concentration until equilibrium is reached. So say you spray a bottle of perfume in the back of the room, and within 5 or 10 minutes you'll be able to smell it in the front of the room. So that is diffusion. That's kind of what we're talking about today with oxygen. Oxygen will be in a high concentration in the alveoli, and we want to look at how much will diffuse across the AC membrane into the tissues. We'll also review the Gauss laws here, so let's get started. So here's a good picture of how our alveoli diffuse. So we have some ventilation here. We need to have the ventilation portion of it as well, because as we have diffusion of oxygen, oxygen starts to metabolize. There's some internal respiration happening in the hemoglobin molecules, and a byproduct of that is CO2. So at the top left of the picture, you'll see ventilation. That's the in with the good, out with the bad. So we have to have that component of it in order for diffusion to happen. So the good air comes in, or the oxygen comes in, it diffuses across the AC membrane into the hemoglobin molecules, respiration occurs, and then the CO2 is a byproduct of that, and that's what gets moved out. Okay, so we have diffusion and ventilation occurring at the same time. In this PowerPoint, we're just going to be talking about diffusion. Okay, so let's look at our gas laws. The ideal gas law says when either pressure, volume, or temperature is constant while one of the other changes in value, the new value of the third variable can be calculated. So you can predict specific changes of temperature, pressure, and volume under different conditions if the amount of gas remains constant. So as long as the pressure and volume and temp are constant, you can theoretically find the value of the number of moles of gas present. And that's called the ideal gas law, or the universal or combined gas law. Next, we look at Boyle's law. Boyle's law is similar to our lungs or to a can of pop. It says that if our temperature is constant, pressure will vary inversely to volume. So with our lungs, remember, as we breathe in, we decrease our interpleural pressure. We have negative interpleural pressure, but our volume increases. Okay, so our interpleural pressure will drop, but our lungs will inflate or increase in volume. The next one is Charles' law. States that if pressure remains constant, volume and temperature will vary directly. So for an example, we're going to use the balloons. If you have a balloon filled with air, you put it in a hot room, the volume will expand proportionally. If you leave your balloons in a car overnight, you'll come back the next morning and they will have exploded, especially if it's really hot outside. Okay? So if the pressure remains constant, volume and temperature will vary directly. The next one, we're going to use a balloon example as well. Now you have a set volume or a constant volume. If you increase the temp, the pressure will increase as well. Same thing as before. If you have a set volume in the balloon, you increase the temp, the pressure will go up. Dalton's law is the next one. Each gas in a mixture will individually contribute to the total pressure created by the mixture of gases. So in our air, We have 21% oxygen, that's at room air. We have 78% nitrogen. We have 0.97% of argon, 1.28% of water vapor pressure, and then we have 0.05 carbon dioxide. So that equals about 100%. So the Dalton's law states that in a mixture of gas, the total pressure is equal to the sum of the partial pressures in each separate gas. Okay, partial pressures. Again, we've talked about this before, but what I want you to get out of this is as you climb in elevation, your barometric pressure drops. The percent of oxygen will remain the same, but our pressure will vary according to the barometric pressure. So that explains why the higher elevations you get shorter breath, because there's less partial pressure for tissue oxygenation. Okay, if we look at oxygen, partial pressure of oxygen is 159, and we take that by 760, or we get that from taking 760 millimeters of mercury, which is our barometric pressure, multiply that by 21%, and that gives you a partial pressure at sea level of 159 millimeters of mercury, and in the atmosphere to use for our partial pressure of oxygen. It's around 100 millimeters by the time it gets to our alveoli, because we have the metabolism occurring, we have CO2, we have water vapor pressure, which aren't as high in the atmosphere. So they're all competing against each other and moving those out. So the partial pressure of oxygen in our atmosphere is 159. Partial pressure of oxygen in our alveoli is usually about so when you have water vapor pressure, you have water that's present in the volume of gas, and it acts like the gas law says it should, and exerts a partial pressure like Dalton's law said. Because alveolar gas is 100% saturated at a normal body temp, the alveolar gas has absolute humidity of 44 milligrams per deciliter and a water vapor pressure of 47 millimeters of mercury, regardless of the humidity in the air. So that water vapor pressure is always 47 millimeters of mercury. That is a constant. So remember that, because we're going to be talking about that here in a minute. So what we can take away from this is that we need to have adequate humidity on our patients that have an upper airway bypassed. Okay, so let's look at our final gas law here. This is the ideal alveolar gas equation, and it explains diffusion. In a minute, we're going to look at the 9 layers of the AC membrane, and this, if you remember those layers, then you can see how the P big AO2 equation works. Okay, so we're going to go through the equation first, and then we're going to dig deeper into the layers and find out how we can fix it and what we can do for this. All right, so the alveolar gas equation explains diffusion. How much O2 is in the alveoli and how much diffuses through the AC membrane to get to the tissues. So P big AO2 is our alveolar air equation, okay, or alveolar gas equation. So P big AO2 is in the alveolar level, and P little AO2 is our partial pressure in our arterial level or our tissue level. Okay, so we're going to start by taking barometric pressure. Okay, so I'm going to let you try these out, and you can either email them to me or we'll talk about it in class. Okay, so on to the AC membrane. I know we did the equation first, but it helps to look at the equation first and then go back and look at the AC membrane to see what things could go wrong. So we have all these layers of the AC membrane. You'll see the alveoli or the alveolus on the left side, and then we have the interstitial space in between, and then we have the capillary bed below it. Okay, so all of these things could go wrong. We could have consolidation. If you go back to your anatomical alterations and look at the ones that are going to affect diffusion, because it's in the alveoli, we'll look at distal airway and alveolar weakening. I know that's a primary ventilation problem, but it might have some diffusion effects as well because the alveoli become weakened. We'll look at excessive air and fluid in the pleural space because that causes atelectasis. We'll look at consolidation, perfusion, increased AC membrane thickness. Okay, so we talked about this a little bit before. We have O2 and CO2 diffusion, so we have to subtract our PaCO2 so that we just look at the pure oxygen and that's it. Okay. Let's talk a little bit about Fick's law. Fick's law says the thicker the membrane, the longer it takes for oxygen to cross. So diffusion of O2 and CO2 will diffuse until equilibrium is reached, usually 0.25 seconds. And diffusion will not occur while you're in a state of equilibrium. Okay, so we have total transit time for blood to move through the AC membrane is 0.75 seconds, but till equilibrium reached is 0.25 seconds. Okay, so we'll take a look at Fick's law, and Fick's law says, well, if you're going to diffuse a gas that fast, that means you have to have a normal membrane. Now, if you look at my diagram, I kind of scribbled a little bit up there. You can see about 12 o'clock that there's a thicker membrane there. So Fick said the thicker the membrane, the longer it takes for O2 to diffuse. So it'll take longer than... Okay, the next one is Henry's law. Henry said that if you have CO2 and O2 diffusing across the same membrane, CO2 is considerably more soluble than O2, so it's going to diffuse 20 times more rapidly than O2. And temperature is a major consideration in this law. Okay, so if you have high temps, it will decrease the solubility, and low temps will increase the solubility. So as a liquid is warmed, the energy increases, or the surface tension increases, and the dissolved gas molecules increase. This causes a molecule to escape faster. So we have to maintain a normal lung temperature whenever we are looking at blood gases. Okay, so we have to keep the integrity of the sample. We want to keep it at room air if we can, but the colder it gets, the more changes we have. The warmer it gets, the more changes we have. So if you... Graham's law is a combination of Fick's and Henry's law. Graham said that the rate of diffusion of gas is inversely proportional to the square root of the gram molecular weight, or lighter gases diffuse rapidly, whereas the heavy gases diffuse more slowly. And we know we see that with CO2, because if you have a diffusion problem, typically you don't have a ventilation problem. If you look at a blood gas with a diffusion problem, the pH and the CO2 are going to be normal. They'll just have poor oxygenation or poor diffusion. So when you put these two laws together, Fick and Henry and Graham all say that the rates of diffusion are dependent upon how soluble the gas is and how thick the membrane is. So we know that CO2 is more soluble than O2, so O2 is increased in the alveoli, and the thicker the membrane, the slower the diffusion. The next thing is perfusion limited gas flow, and that's easy enough stated. If you don't have blood flow, you have no perfusion or diffusion. Diffusion limited gas flow, diffusion across the alveolar wall is a function of the AC membrane. So you have those lighter gases like carbon monoxide, carbon dioxide that move through the AC membrane quicker. So if we're looking at O2 or diffusion, we have to look at, is it perfusion or diffusion limited? At rest, the diffusion of O2 is perfusion limited, meaning we have adequate blood supply to help transport the oxygen to the tissues. But in a disease state, the transfer of O2 is diffusion limited because you have a thicker AC membrane or you have fluid in the interstitial space, and it's going to be diffusion limited. Okay, so you can read through the summary here. This just kind of sums it all up. Remember, diffusion is a concentration or movement of a gas from a high concentration to a low concentration. Each gas in a mixture diffuses according to its own individual partial pressure gradient. Diffusion ceases when equilibrium is reached. Gas laws help us understand that gases are composed of help compose the barometric pressure, and the partial pressure of the gases in the air, alveoli, and the blood. So what happens to the AC membrane in a disease state? Okay.